Alright, in this video I want to show you how to determine if a polynomial equation has at least one real solution. You know, an equation could have real solutions, it could have imaginary solutions, it could have no solution, period, depending on the type of equation you're dealing with. But I'm going to give you a little review. Some of these items you might not need for this particular video, but it's something that you should know. So first of all, let's look at the definition. A polynomial function has this particular form right here. Notice the powers on the x are decreasing. The coefficients, a sub n minus 1, and so on, those in this particular case we're looking at real coefficients. Those are real numbers, and obviously the exponents cannot be negative. They have to be non-negative. Okay. Now a polynomial equation takes the form p of x equal to 0. So if I just take this expression over here, set it equal to 0, it becomes a polynomial equation. So let's look at the relationship between the two. So let's consider an example. Look at the equation x squared minus 9. If I wanted to solve that, that's a quadratic equation. So I could just factor this. One side is 0. So I factor it. X minus 3, x plus 3. So the values that are going to work here, that'll make this 2, will be x equal to 3. Or x equal to negative 3. Those are the solutions to this equation. Okay. You put a 3 there, 3 squared is 9, minus 9 equals 0, so it checks. Negative 3 squared minus 9 is 0, it checks. Now, polynomial functions. Over here on the right, I have graph y equal x squared. This could be f of x, or since I'm dealing with polynomials, I can label it p of x. Okay. So if I wanted to know what the zeros of this polynomial are, they would be 3 and negative 3. Okay, 3 and negative 3. So the zeros are simply those values such that if you replace the x by those numbers, you get 0. 3 squared is 9, minus 9 is 0. Okay, so in terms of a point, that would be the point, say, 3, 0. Negative 3, 0. Okay. So the graph passes through the point 3, 0 and the point negative 3, 0. And 3 and negative 3 are said to be the zeros, for obvious reasons. Okay, so if I were to sketch the graph, this point right there, say, would be negative 3, 0. This point over here, right there, on the x-axis would be 3, 0. And this point down here, where the graph crosses the y-axis, that would be the y-intercept, and that would be the point, say, 0 and negative 9. Okay. So you can see the relationship. So when you're solving a equation like this, if you set it in terms of a graph, okay, so if one side is 0, you take this right here, this part right there, and set that equal to y, and you sketch that on a calculator, the x-intercepts, which generate the zeros, will also be the solutions to that particular equation. Okay. So that's information hopefully you know already. The other thing I want to point out to you when you're dealing with a polynomial function is that the degree of the polynomial, which in this case is n, tells you how many zeros to expect. Okay, so if it's degree n, you expect to have at most n distinct zeros. They could be repeated zeros, but at most you would have n. So in this particular case here, y equal to x squared minus 9, that's a second degree, okay, highest degree term. You get the degree from that is 2. So you would expect to have at most 2 distinct zeros. Okay, they could be repeated zeros. Okay, for example, something like this, y equal, let me just make it x minus 3 to the 10th. Okay, if I were to actually multiply this out, my first term would be x to the 10th. So this would be a 10th degree polynomial. So I would expect to have at most 10 distinct zeros. Well, in this case, I have 1 0, which is 3, but it's repeated 10 points, so it would be a 0 multiplicity 10. So 3, we say 3 would be a 0 of multiplicity 10. Now the other thing that's convenient to know is this, that if you have the graph, say I want to look at the graph at y equal x to the third. Okay, that's a very basic polynomial, and the degree is 3. If I were to graph this, the graph would go something like that. Okay, I pass through the point, the origin 0, 0, so 0 would be a 0 of that polynomial. Now if I stick a negative, okay, I stick a negative in front of this, and I want to look at y equal minus x cubed, this would go the opposite way. So instead of going up, it comes down this way. Okay, so x cubed, y equal x cubed goes this way, and y equal negative x to the third comes this way. Okay, so the graph is either rising or falling depending on the coefficient of that high degree term. Now if I look at say y equal x squared, that's a second degree. If I were to graph it, this would give me something like that, a parabola that opens up, a vertex at the origin. Okay, if I stick a negative in front of this, then the graph opens downward this way. Okay, so if the graph crosses the x-axis, it's going to have a 0. So this particular one over here has 2 zeros. It crosses the x-axis twice. This one crosses once. Okay, so there's 1 0. Now if the graph is up here somewhere and goes like that, obviously it doesn't cross the x-axis, so no zeros. So if it's below like this, no zeros, and so on. So another thing that's important to know is that if you're looking at a polynomial graph, the graph of a polynomial, the graph of the polynomial is going to behave like the graph of the lead term. Okay, so we saw what the graph of y equal x to the third looks like. If I look at x to the fifth, the graph is similar. Okay, goes like that, passes through the origin though. If I put a negative there in front, it's coming down this way. Okay, if I look at x to the 7th or x to the 9th or x to the 11th and so forth, the graphs are going to be similar. So just to make it short here, if the lead term has an odd degree, then you would expect the graph to be rising like that. Okay, if this lead coefficient here has an odd degree exponent and it's positive. Now if it's negative, just the opposite, it comes down. Okay. Now if the lead term is even, the exponent is even for that term. Say this is a 3x to the 4th or a 3x to the 6th and so on, then you would expect the graph to go up at one end and up at the other end. Okay. The odd, it goes up at one end, down at the other one. Or it could go like this and like this. Okay. Where if it's an even exponent, it's going to go up at both ends if the coefficient is positive, or it's going to go down at both ends if the coefficient is negative, just like we saw with y equal x squared and y equal negative x squared, and so on. Okay, so one of the things, and then I want to point out to you, when you're solving an equation, okay, and this particular video again is not really showing you how to solve the equation. I do have some videos where I go through the solution of polynomial equations, doing it manually by finding the zeros and using Trolley method to factor it and so forth. This particular video really is just to determine whether a polynomial equation has a real solution. Okay. So again, anytime you're solving an equation, a polynomial equation, you can solve it on a graphing calculator or determine whether you have a solution by looking at the graph of that. Okay, so in other words, if I wanted to solve x squared minus 9, of course this is very, very easy, I just did it a while ago, I could graph y equal x squared minus 9. Okay, so in other words, what I'm saying, if you want to solve, say, p of x equal to 0, if you want to solve that, then graph y equal p of x. And whatever zeros you have for this graph are going to be the solutions to this equation. Okay. So those are some ideas that hopefully you're already familiar with. So let's get down to what the video is really about. It says determine which of the following have at least one solution. This is the main thing for the video. Determine whether it has at least one real solution. But we also, in some cases, we can tell whether it has no real solution. Okay, so here's what we'll do. Let's look at x cubed minus 2x squared plus x minus 2. Okay. Notice the lead term is x to the third. Positive, coefficient is positive, so I would expect the graph, okay, and it doesn't have to pass through the origin, but it would go something like that. So that is definitely going to cross the x-axis, whether it's up here, down here, because it's going up this way. Or if the coefficient is negative, it would be coming down this way. Either way, it's going to cross the x-axis. So if it's going to cross the x-axis, it's going to have at least one real solution. And this one does. Okay. Now, I'll give you what the solution is. X equal to 2. So it has one real solution, and it actually has two imaginary solutions. Okay. again, in this particular video, I'm basically just showing you how to determine if it has one, not necessarily how to find it. Because I do have some videos on that that you can look at. So this one, yes, does have one real solution. And it has imaginary solutions also. But the focus here is either real or no real solution. Let's look at the next one. X to the fourth minus 5x squared plus 4 equal to 0. Okay, so this one, notice if I were to look at the graph of this expression on the right side, the lead term has an even exponent. The coefficient is positive, so I would expect the graph to go up at one end and up at the other end. Okay. Now, if that coefficient had been negative, then I would expect it to go down and down at both ends, and then in between there it could loop like this. Okay, depending on the degree. So on something like this, unless you actually graph it or figure out by plugging in numbers, you can't really tell just by looking at it. But you can, if you're just interested in finding whether it has a real solution, you can look at the graph. Okay. Okay, so here I have all of them already entered just to save time. So I'm going to look at number 1 and look at the graph of that one. Okay, I have it highlighted, so I'm going to set it graph, and you can see what the graph looks like. You can see again, because it's odd degree, it goes and the coefficient is positive, it goes up, and you can see it crosses right there. Okay, now you can look at the table here. I get second and then graph, accessing the table, and you can see here that when x is 2, y is 0. So that tells you that, as I mentioned, that x equal to 2 is a real solution. Now this is third degree. This is third degree, so you would expect it to have at most, that's what the theory tells you for polynomials. If it's third degree, you expect to have at most 3 zeros. Okay, 3 distinct zeros. They could be repeated, as I mentioned earlier, but in this case we only have x equal 2. Okay, so the first thing we did by looking at the degree, it was odd degree here, so we knew it. This one here, the second one, because it's even degree, it's not for sure whether it's above the graph or below the graph. So again, let's look at the graph. So now let me take this one off, hit enter, and let's go to the next one. Oops. Okay, so hit enter to highlight that one, and then I'm going to hit graph. And you can see again, as I mentioned, it's even degree. X to the fourth has the next one to the fourth, so this is fourth degree. The left side is a fourth degree polynomial. So you would expect to have at most 4 real zeros, or 4 zeros. Okay, so notice it. You can see from the graph that it crosses to 1, 2, 3, 4. Okay, so there you have it. Now the table will give you exact answers. So if I get second, access the table, then you can see here when x is equal to minus 2, y is 0. Okay, so that's a solution of the equation. Notice at negative 1, you get 0 for the y. That's another solution. Okay, look at 1 and the y is 0. There's another solution, x equal 1. And then again, x equal 2, y is equal to 0. So those are solutions. Okay. There's zeros to the actual polynomial graph, but there are solutions in this particular case to the equation. Okay, so it has 4 real solutions: 1, -1, -2, and 2. Okay, let's go to the next one. Okay, notice this one. The first term is x to the 6, so the exponent is 6. It's even, and it's positive coefficient, so you would expect the graph to go up at both ends. Okay. Go up at both ends, so it's go like that, like this, and then you would have it loop in here a few times, or it could be just a parabola. Look like a parabola, goes up. And if this graph is strictly above the x-axis and opens up, it's going to have no real solution. Or if it's below and opens down, again it'll have no real solution. Well, in this particular case, without looking at the graph, I can tell that it has at least one real solution, because every term has an x. Okay? Notice every term has an x. There's not a constant on this side, and on one side is 0. So it should be clear that if you replace the x by 0, you get 0. 0 is equal to 0. So this one does have one real solution. Okay, so remember the instructions said determine if it has at least one. So this one does have at least one. X equals 0. Now, if we wanted to go further, we could look at the graph. And let's go deselect this one, and let's select this one. And so now we're going to graph this one. So hit graph. Okay, so you can see that it has the look of a parabola, so it does go up at both ends. Okay, and in the look of a parabola, and you can see that it appears to cross right there, which is close to the origin. So it looks like x equal to 0. Could be a 0 of the graph, which would be we already said is a solution to this. So it's clear that it should pass at 0, 0. And then there's another 0 right over here somewhere close to -1. Okay? So if I wanted to find it, see, I've answered here, it does have at least one 0. Okay? You can see from the graph that it actually has 2. So again, this is just extra here, so it's not really asking for this. So if I want to find out what that is, I can go to second calculate, and what am I calculating? I want to find the zeros of the graph, which would be, of course, solutions to this equation. So hit number 2, and then the way this works, notice on the bottom here it asks you for a left bound, so just put the cursor just to the left of that and hit enter. Now notice it asks for a right bound, so go past it to the right, hit enter, and then it asks you for a guess. You can just ignore that if you want and hit enter. So this tells me 0 at x equal -0.9520017 and so forth. Okay, y equals 0. So you can see this y equals 0. So this is telling you that this is a 0 of the polynomial, -0.9520017. So this actually has 2 zeros, real zeros. Or in this case, since we're solving the equations, we say 2 real solutions. Okay, it does have at least one, and using the calculator I found both of them. Now the other 4, see, at 6 degree is degree 6, so you would expect to have at most 6 zeros or solutions. Now the other 4 turn out to be imaginary. Okay, so you could find those using trigonometry, more advanced techniques, but in this particular case, that's as far as we go. Okay. Now the last one, we have 3x to the 8th plus 6x to the 6th plus 7x to the 4th plus 11x squared plus 22. Okay, so one of the things you have to keep in mind that if in this particular case we're looking at this part, the right side is 0, so this would be your polynomial function if you're looking at a polynomial function. And the thing you want to look at is the exponents of all the x's. They're all even. 8, 6, 4, 2. The 22 is constant, but if I want to put an x there, it would be x to the 0. Because x to the 0 is 1, and 1 times 22 is 22. So they're all even. So here's the deal. If all the exponents on the x's are even, and all the signs are the same, all positive or negative, then there's no way that you can have a solution to this equation. Okay? Because notice, you plug any number in for x, I don't care what it is, whether it's a negative number or a positive number, because the power is even, it's going to stay positive. And then you're adding a positive 22 to that, there's no way you're going to get 0. Okay? So the only thing you want to test is x equals 0, a solution. Well, the only way x equals 0 would be a solution is like I said in the last example, is if all the terms have an x. Okay, so in the number 4 has no real solution. Okay, since it's degree 8, you expect to have at most 8 distinct solutions, and you do, but they're imaginary. Okay, so you would have to get them by using advanced techniques involving trigonometry. Okay, this concludes the video, and like I said, I probably gave you more than you needed to know to solve what I asked here. Okay, but this will conclude it. I'll follow up with some more videos, and as usual, if you have any comments or any suggestions for videos you want to see, please post them, and you subscribe to the channel, then I will respect your request, and hope to see you in the next video. Take care.